So, good morning, everybody. We are happy to start the new series of seminars for this year. We welcome with our wish card for this year. It was for our institute a particular fruitful year. That's why before starting the presentation, you will allow me some. Oops, here we are. Okay. Technical problem. We don't have a. The proper. Okay. So I should put this aside. Okay. So here is our progress in the last year. We sent that to the academy authorities this year when we were asked for our report. You can see that definitely there is a progress that steadily increases in the last years. In particular, for this year, I have just bulleted some of our achievements, and certainly, as we do every year, we will today, I think, Thanas, or tomorrow, we will have the annual report on our webpage. It is already there.
Yes,
so you
the
can
webpage.
on our webpage, and we will distribute it around also in paper as we do every year. So one of these research projects that we have carried out in our institute this year is the topic of our today's talk. Okay, you see the title, you already know that. It is about bar-free grand design spirals. We're gonna speak about the dynamics of two-armed spiral patterns. And this is a very old story that goes back in our, let's say, group with Professor Kontopoulos and other collaborators, Preben Grossbull and Garching and several others, actually, that we started investigating in the early years for me, or even more for Kontopoulos, of course, etc. But okay, so the contribution of this year was that we have identified dynamics that we are steadily claiming that take part on disk who has this kind of morphology. We have found that in some kind of modern n-body simulations. And this was a work that we carried together with Periklis Okalidis, who is now here in the audience. Most of you that have followed other seminars, you can understand what is on your screen. That you have, you probably see, or you don't see me. If you, there is an audience in the room that looks to a projector which is in this side, and the audience is over there. So sometimes I'm looking peculiar, sometimes this direction, sometimes this direction, because I point to the projector. So, okay. So we speak about objects of this kind, like what you see here in our galaxy that we found in the internet. And this is a grand design, a two-arm grand design spiral galaxy that does not have an obvious an apparent barred structure in the center. And I will do an introduction, and in the close to the end of the second half of the talk, I will present you the new results. So we have to understand to say some basic things about the morphology of these objects. Probably when one speaks about spiral galaxies, many people recall M51, for instance, who has a companion. Okay. But there are some details that is interesting to underline for this particular presentation. So we do not speak about barred galaxies, which are grand design. They have an m equal 2 component. The bar is an m equal 2 component, and then a bisymmetric spiral pattern that sometimes emerges out of the end of the bar. Sometimes it is a little bit farther out. But what you see here are three types of morphologies. To the left is MGC 2997, famous galaxy because it was in the cover of the Bini and Tremaine initial edition, which in the optical, it is clearly some non-barred galaxies. In the near infrared, there is a kind of oval distortion in the center, but you do not call it a bar. And what is also interesting that, as you probably know, in the near infrared, where we observe the old stellar population, disk old stellar population, then several faint details, sometimes not that faint, parts of arms, etc., are much more fainter. So the grand design is enhanced if you look at the disk old stellar population. And then we have the other kind of galaxies like 3225, where when we look at the optical images, then you don't see grand design. But very basic image processing, the grand design is revealed, is there. And here we have, for instance, an optical image of 3223, but then we go to the near infrared, and then what we do is just we correct for projection effects. We deproject the galaxy to see that face on, and then we divide or we subtract an abscissymmetric background. And then we see that in the underlying stellar population, there is a bisymmetric spiral pattern. And what is also very interesting is that this is a logarithmic one. We care about the old disk stellar population because there are the K and M giants, and they are the majority of the stars. They make up the vast majority of the mass of the galaxy. So if one thinks in terms of potentials, then you can think about the potential well determined by this morphology. So stars that rotate around the center of the galaxy have the time to feel the potential, go down to the potential well they will find, and hence the local density and structure of the galaxy, the morphology. Now, I spoke about logarithmic spirals, and since the audience here at least is quite diverse in terms of the thematic they are working on in astronomy, what a logarithmic spiral means is that the pitch angle of the spiral remains constant, and the pitch angle is the angle that the spiral, the red curve you see there, forms when you, at the same point, you pass a circle, like what you see on your screen over there. Okay, this I is the pitch angle, and wherever you put a circle, then this angle will be the same. So it is simply, if we express it in polar coordinates, R is E in the power of A theta polar coordinates, and A, it is related with the opening of the spiral. So we have tightly round spirals where this pitch angle is small. You hardly sometimes you can, if it is 1 degree, for instance, you hardly can find visually the difference of a circle, and then you can have 20-30 degrees pitch angles, which is the pitch angle we encounter in galaxies. So if, of course, this is always an unequal 2 pattern, and if this pitch angle is 90 degrees, then we have a bar. Just note that there are, in galaxies, we do not find pitch angles between, let's say, 35, 40 degrees and 90 degrees. All the spirals we find are up to, let's say, let's put an upper limit, 40 degrees. Maybe 30 is a better number, but okay. And okay, another note, it is that this logarithmicity, if you allow me the term, is true for all spirals but for many grand design bisymmetric spirals for the most, but it is not true for the spiral arms in bar spiral systems. There are dependencies. For instance, what is the distance between the end of the bar and the assumed co-rotation radius? Or if we have two different systems, two different modes rotating with different pitch angles. All these are taken into account. There is work in progress on that, in classifying observed morphologies and trying to associate them with underlying dynamics. We have a number of several tens of galaxies now that we have actually observed here in Greece with Aristarchus, and it is one of the other projects of the Academy this year is about that, and soon we hope we're going to have also published results on that. So I'm speaking on non-Barth galaxies, and this logarithmicity is something that is quite common for these objects. Okay, and again, for those that of you that you are not familiar with the subject, barren spirals are considered as density waves. And what practically means is that as they rotate around the center of the galaxy, they do not stay on the arms of the galaxy for all the time. They cross the arms, and then it is like a density wave. They stay for longer time over there. In the coming slides, I will explain that, I hope, a little bit better. So the difference between a bar and a spiral is mainly on you can think of ellipses that are concentric and they build a galaxy. And if they are aligned along an axis, then this is a bar. And then if you assume a law of precessing for successive radii, then you can build a spiral. This is the notion of the density wave. And then here we have this, we call it as persisting ellipsis flow. It is a term that is not maybe not very you don't encounter it in papers, etc. But it's something that we have coined inside this institute. This is what we mean. Precessing ellipsis flow is a flow that goes through the arms of the spiral galaxies. And if this happens, then we have a differential rotating disks, so like the solar system somehow, but it's a general differential rotating system. You can imagine stars that are rotating faster, close to the center of the galaxy, and slower as you go farther out. And then you build the spiral. The spiral has its own pattern speed that rotates as a rigid body, and then this is the way that in such a system everything rotates, but the spiral is not destroyed. If contrarily, if you assume that the spirals are composed by stars that remain the whole time on the spirals, it is just, and you do the calculations, very simple mathematical calculations, you will realize that very soon, very fast, these spirals will wind. They will destroy themselves, because as the closest to the center stars rotate fast, and the other one, the farther away, slower, then they destroy the spiral itself over a few dynamical times. And this was also the motivation for thinking of a theory that goes sustain the observed spirals, because we see spirals all over the universe. Okay, so okay, and here just to show you exactly how it is in a model. This is a spiral model. Doesn't matter exactly what it is. What is the potential one? I just picked up a star that rotates with the same rotational velocity, angular velocity like the sun, and then this model has a spiral in equal time steps. I registered the time steps, and then you see that how longer the blue points remain hence the spiral, while in the interarm region they go very fast. They go in the spiral, you see that, then they cross very fast, find the other spiral, etc. And I use that this slide mainly in talks for a broad audience, just to point that the whole the time that humans are on Earth are just between two of these blue dots. Dinosaurs were here when the sun was in the same place. Okay, there are some basic assumptions for this, the results I'm going to present you. That, as we said, disks are differentially rotating, that there is a pattern speed of the structure, the spirals in that case. I'm going to say the same for the bar, that it is one pattern speed, because as I noticed before, there are models claiming successfully in many cases that in galaxies, in real galaxies, we have two of this kind of pattern speeds. But here, not only for simplicity, but because it is one pattern speed can make the trick and model the studied structures, the bisymmetric spiral. And also that for the first part of the talk, at least the underlying potential does not vary very fast over time. So if this doesn't happen, we do the assumption that we have a time-independent potential, and then the next step is that one can think of the galaxy as Hamiltonian systems. It's an assumption that has been done more than half a century ago and has given very basic, I would say, results. And if we do that, here is the Hamiltonian we have, and the whole trick is in the potential we're gonna assume, and the pattern speed that the spiral will rotate. So this part is the effective potential. And okay, since we are in autonomous, as we say in the nonlinear dynamics community, autonomous Hamiltonian system, then the Jacobi constant is, we have an integral in the rotating frame of reference, and then this is essentially what is the energy. Vaguely, we're gonna call it also the energy. So these are the basic assumptions for trying to calculate orbits in these systems. So we have the Hamiltonian, we have the system of our equations of motion, and there we can look for solutions. We will be our trajectories, our orbits, and the general form of a potential will be like this. We decompose the potential in an axisymmetric background, and another term that will describe the spirals or the bar, if we would like to investigate bars, and in the rotating frame of reference. And what we find, first of all, in the axisymmetric background, because, okay, we study the spirals, but if we think of the potential well, it is the axisymmetric background, and then the spirals can be somehow a kind of perturbation, are much less mass accumulated on the spirals. So we're gonna think of three kinds of orbits. The basic one is the circular family of periodic orbits, which one can just find them very simple with very simple calculations, analytic calculations, and it is, as you see there, it is directly related with the rotation curve of the galaxy. We have the rotation curves, and then we have the potential. Then we can find the circular orbits. They make the backbone of our dynamical system. They are very important. This is a very important family. I'm saying again that, as underlined there, we speak about the axisymmetric background. Then there are other orbits that are not periodic. We go close to the initial conditions of the periodic orbit, we integrate, and we find orbits that can be described with the epicyclic approximation. What this practically means is that you can imagine the star going around the center of the galaxy, but simultaneously doing a radial oscillation, which is the epicyclic one. And then this one combines these two frequencies, the one that rotates around the center of the galaxy and the other one that is associated with the radial oscillations. And then we have a third kind of families, the resonant periodic orbits. As we have their resonances, since we have two frequencies, maybe we can see that the next slide here, you can see the relation on the left. Kappa is the epicyclic frequency, then in the denominator we have the rotation, the axis symmetric in the rotating frame of reference with omega s in that case, and then this gives us resonances, 2 to 1, 4 to 1. Then we have the co-rotation. It is in the axis symmetric potential, the distance from the center that where the star and the pattern, the spiral, rotate with the same angular velocity, and then we have 4 to 1, 3 to 1, 2 to 1, etc., 1 to 1 outside co-rotations with the outer resonances. The most important of them, the most frequently encountered in textbooks and papers, are the Lindblad resonance. All of them are called Lindblad resonance, but actually the 2 to 1 and the minus 2 to 1 are the inner and outer Lindblad resonances. And what does it mean? Simply that when the star has performed a circle around the center of the galaxy, has performed two radial oscillations. So these are the resonances. And the resonant periodic orbits I have mentioned before, what are they? They are solutions of the system of the equations of motion, periodic solutions that are introduced in the system exactly at the radius, in the axis symmetrical waves potential I continue to underline, where the frequency is 2 to 1, 3 to 1, 4 to 1, etc. There are new solutions introduced in the system, new numerical arithmetic. Well, here we can do an analytic, but this goes also to the full potential. New solutions in the system, and these are non-circular. Their shapes is associated with the resonance they are introduced in the system, and they are the resonant families of periodic orbits. This is the tools we have in our hand to start building galaxies. And here is just a nice graph of one of the spiral potentials that satisfies the logarithmicity I was speaking about, used for the first time in a paper by Kontopoulos 40 years ago. But okay, here I have a table, let's say, a map of the periodic and non-periodic orbits that one can find in the system. Also now, also when the full potential is there, we have the periodic orbits. They are very important for dynamics of the system, for dynamical reasons. They structure the phase space as an important property. So if we know where periodic orbit is, we know in the landscape, the phase space, the surrounding, and then we can assess how much we can count on the surrounding this periodic orbits. And then we have the non-periodic orbits that are the quasi-periodic orbits or regular orbits that stay all the time close to the periodic one, and the others that the chaotic, that they diffuse in phase space and they visit all phase space which is available. Some of them delay to do these diffusions. These are for several reasons, and they are our sticky chaotic orbits. So this is all kind of orbits that we have in our hands. And okay, Padelis asks.
Just forgive my ignorance in dynamics thing. No. What's the structural reason for the resonances? Because I hear them also.
What I didn't hear.
For the resonances.
Yes. What?
Because I hear, what's the structural reason why they exist is an aspect of the differential equation with this potential.
Oh yes. Yeah. Okay. Yeah. Yeah. Well, there are. You have. You can in this approach. You better think of a system of differential equations.
Okay.
Okay, and you find solutions. And then there is a well-known phenomenon in dynamics, the phenomenon of bifurcations. Okay, and where do these bifurcations are new solutions that are introduced in the systems, but where should I look for them? Now here we have a hint, you know exactly where to go, you know, you have tools, you will see in a while, where you see in which energy, Jacobi constants, you will expect to find these resonant periodic orbits. You go there, you have tools, you find new solutions in the system. Okay, there are periodic solutions of the system of differential equation, or the equation of motion of your Hamiltonian. Okay, now here we start going in the essence of what we're gonna say today. To the left, you see a Kalnas 1973 sketch that was practically describing what I also described in the beginning using Kalnas figures, how precession ellipses support a spiral. However, if you go to the real Hamiltonian, you have a Hamiltonian with a spiral potential, etc., and you start integrating orbits in a spiral potential that has, let's say here, 30 degrees pitch angle like this, then you realize that the sketch on the left cannot be applied all over the extent of the disk in terms of resonance, going from the center to the outer Lindblad resonance. And this is mainly due to the shape of the trajectories. When you go to the 4-to-1 resonance here, then you find squares as the stars perform 4 radial oscillations, completing 1 revolution around the center of the galaxy. And this introduces new stuff, at least tells you that you cannot think without any caution about a precession ellipsis structure that dominates all over the disk of the galaxy. And then there are some other stuff that comes in the system, mainly for bars, but also in a smaller extent to spiral potentials. When you approach co-rotation, the amount of these chaotic orbits I just said that exist increase. And then if the perturbation is strong, if you have a bar, for instance, then you have chaotic zone. Then you have to go far away to find again periodic orbits, regular that will support regular flow, so quasi-periodic orbits around them, farther away, and contribute to supporting this part of the spiral. In this case, is a barred spiral system. So actually, what I want to say, I summarize with what we see in the middle again. Here I had some elliptical orbits. They change in the rotating frame of reference, supporting the red spiral. When you go the cross-corrotation, then the sense of rotation of the orbits changes because of the sign that changes over there. You cannot have this simple, let's say, concepts, this simple sketch all over the disk. So if you see such a figure, then initially this implies that we do not have crossed corrotation. Okay, let's go further away. Okay, here. And speaking about order and chaos, here is a typical Poincaré cross-section, just mainly to show you how this look on a Poincaré cross-section, the invariant curves surround the periodic orbit. X1 is the name of the main family of periodic orbits, also in bars, also as well as in normal spirals, non-barred spirals, precession, non-precession. And what I want to tell you is that the amount of chaos that you find in these systems, it's related with the strength of the perturbation, how strong the spiral or the bar is a stronger, much stronger perturbation than the spiral, then there you find a lot of chaos. As you reduce the amplitude, then chaos, the role of chaos is not that important. And here are, just to show you a tool related to the question of parallelism before. Here we have an index, goes back to a norm that describes the evolution of the stability of these orbits. The orbits are organized in families. As I told you, here to the left are the circular family, and you see that in this diagram, it is for the axisymmetric part of the potential. The radius is directly associated with the energy. So you see that when you have this, they have an oscillation, and each time they touch the axis 1, alpha is the non-index 1, then at this point, there is where we're going to look for the new family that will be introduced in the system. And to the right, we have added the perturbation, this is the real thing, and then you can see that we have new curves like this one here that are introduced in the system. We have new families, we know how they are, and we can follow their stability. So what is now, when we come to the real objects, to the galaxies, we cannot, by observation, simply point to the pattern speed or the rotation radius. It's equivalent, and also the other resonances. We don't know what is the strength of the perturbation, the amplitude of the perturbation, and what is the pattern speed. We cannot easily also have data for starting doing these assumptions. It was a big help in the 90s that the near-infrared images came into the game, because we have less problems with the dust there and population effects and all that stuff. We don't know also the distribution in any case of the dark matter. Thus, modeling is needed. And just going a little bit faster now, you see very, very old results. We tried many years ago to do self-consistent tests. We did assumptions. Since we don't know neither the amplitude nor the pattern speed of the spiral, we do assumptions about that, and then we compare the imposed density, the one that one can calculate from the Poisson law, with what our orbits will give. And it was, the result of this study was the following, that in open spirals, the nice spirals that we see in the atlases, in other words, they can be modeled with perturbations that in the forces, the amplitude would be 5 to 10, up to 12, in some case percent, but let's of the order of 8 to 10%. And the pattern speed was as fast as to put the end of a bisymmetric part of the spirals close to their ends. So for instance, here we have the M51, I told you before. You can see that this arm, and if we go to the other end, has a bisymmetric part. Then things change. Here you have an angle, let's say, we call this the elbow of the arm. It's not the same. Here, okay, in this case, we have also the companion, and things farther out are not related to the density wave theory, but in the center it is. In order to reproduce all that stuff, you had to assume that the end of the bisymmetric spiral pattern was here and there, and then you could have just a model like this, which reproduces many of the morphological features of the galaxy. Okay, this means that spirals rotate slowly, and then corrotation is not at the end of the spirals or on the spirals, on the spiral arms, but farther out. And since the amplitude is of the order of 5 to 10%, then there is not so much chaos present over there. This is consistent with observations. This is what also observations tell us. And okay, this restriction of the extent of the spiral in terms of resonance was not that obvious, at least when the pitch angle was very small. So galaxies like the one you see on the left there, the projected image, it's also almost face on this one, but okay, whatever corrections we could do, we have done, and the C4088, then the pitch angle can be assumed there as being 1 degree. Then these effects of the rectangular-like periodic orbits, the fourth one resonance and all that stuff, were not that severe. Also, the amplitude would go down to 1% from 10%, and so this could continue. This structure could continue its extent towards corrotation or to the outer resonances. Okay, this is what we had. Then, in the next step to this discussion, we went to follow also the behavior of the gas. And in the beginning, what we did is, since we have a solution, we believe it is okay for the stellar dynamics, for the potential, we have taken this potential, making also some adjustments to be closer to the observed galaxies, like adding to the main m equal 2 component and m equal 1, like in this case. You see that one arm is extending to longer azimuthal distances, at least, and farther away from the end of the bisymmetric spiral pattern, which in this case can be identified as being here and there. You see this and this arm, and then you have an extension that is not there. So we have added an m equal 1 component in our potential. Big deal. But the point is that under this assumption, the features, the morphological features that were not that obvious in the optical, were present in our gaseous models. These are SPH models that we had.
So the gas only responds to the potential.
To the potential. Exactly. Yeah, exactly. So we have a gas that responds to the background potential that
so the mass of the gas is like not
okay.
By itself.
But if you have a response model, you don't care about the mass so much. You know, this is a gaseous disk. You have a potential. It's not self-gravitating at this kind of models. But what was important is that in some cases also secondary details, secondary feature details of the models were there. So you see that we have the bisymmetric pattern. We have this bifurcation over there, I3 we call it there, B1, B2 designates the end of the bisymmetric pattern. Then we have an off phase with respect to the main pitch angle of the main spiral extension towards corrotation and all that stuff. And however, this gave us also nice agreement with other other assumptions, theories, and observations that, for instance, if you model in this environment, you can reproduce, for instance, the succession of the maximum of the shock with respect to the young objects that are born in the spirals. Here, for instance, you can see to the right, the dust lanes is where the gas is compressed. That's why you have the maximum absorption of the light over there, and they appear as dust lanes, dark dust lanes. And then the H2 regions that are about bringing new stars in the galaxy are these reddish objects that you see ahead in the sense of rotation of the spiral. So the gas is coming there, is compressed, star formation is taking action, and then the open cluster and the H2 regions are observed ahead of that. So this modeling is also consistent with that.
What's the time to cross from the dust lane to the...
This is just of the order of few mega years, I would say. To cross, we say, but
that's enough to initiate
just to tell you to give you this time scale, the stars are born in open clusters, okay? Dynamically, an open cluster over there is a cluster, is not dissolved for, let's say, 50 to 100 mega years, then wouldn't be there to observe it. So it's much smaller time scale with respect to the time scales we were discussing before about rotating around them.
Also, the time scales of the dispersion of the molecular cloud is around a few times 10 to the 600, 10 to the 7.
Yeah.
That's the time constant. Stars are born out of molecular clouds. The dynamical time for the clouds to disperse because of star formation is around 10 to the 7.
Yeah.
A few times 10 to the 6.
Okay. So, okay. In some cases, actually, we had observed also the existence of double spiral patterns, which that by the time we have observed that we didn't care, but then it seems to be a whole theory for the weak, for the faint, not weak, for the faint extension, the green extension that you see to the right. It's the subject of another talk. It has to do with what much later we found, and we call it chaotic orbits, etc. But okay, okay, here we claim in some cases that you can combine these two theories to have a system of two spirals, one within the other, each one of which is explained with a different dynamical mechanism. Okay, but okay, it's not just to show you some cases where the theory applies and can be combined with other existing theories of spiral structures. Now, the standard argument that it was against all what we have here is okay, but look, you have done all these assumptions, and above all, the assumptions that people didn't like was that the potential is time independent. So we have secular evolution. This is not gonna take place. Things will gonna change. So you cannot apply, despite the nice similarity, nice matching that you have between them. Okay, this was justified criticism. We have accepted. And what would be the solution? The solution would be to try to do n-body simulations and study the same things. And back to 1999, as you see there, we have started with Dave Kaufman a series of modeling, and this is one of the cases we could reproduce the dynamics we were finding in our analytic models. Look at the velocity curve, which is up in the left, in the upper panel of the left figure over there. Okay, it is
Without the dark matter?
yes, it is dark matter is there, but exactly this was the point. We have found, okay, we could realize that if you had a disk maximum solution, if you have given the whole light to the luminous matter, then these systems go bar unstable immediately, and then you get the bar. You have very nice dynamics, very interesting things, not the kind of morphology we would like to study, the non-barred bisymmetric grand design spiral. Then we start giving more to the dark matter in the inner parts, and over there you can see that there is a bulge, which is the dotted curve, but the two others make the rotation curve, the total rotation curve, which is the upper one. The second to the, forget about this here. It is just
giving it a bit flatter when you go to.
No, it's a typical, it's very, very nice, very typical rotation curve for a galaxy. Not a problem with that. The whole trick, however, started with balancing luminous and dark matter. We went away from the disk maximum solution, we couldn't do else. And then we have started seeing modes that were on our systems. You will see this kind of figures in the next transparencies just for I can explain you details how we calculate that later, but think of iso-omegas landscapes that are cut, and they give this iso-omega curves. And then we can see that if we consider everything, then we have several modes, several m=2 patterns. This is for the m=2 structure. For the stars, in this case, you could see several things. But if you exclude, let's say, 20% of the noise, if you want, then you would see well-structured patterns that are extending between the 2-to-1, this curve, and the 4-to-1, this curve, resonance.
A small remark, Panos, just aside. Obviously, in these systems, the dispersion, the Z dispersion of velocity is a small fraction of the
Okay,
rotation.
well, let me tell you, this was a two-dimensional modeling.
Right, okay.
And not only this, another drawback was another, let's say, we didn't have by that time the computing.
Because you know the story we're discussing in the high redshift that you get this dynamically
voltage
with very big dispersions along
Okay,
the Z.
no.
So.
First of all, there are two dimensions.
Yes,
Second, the aim is to model
Yeah.
nearby galaxies or the local universe
Yeah.
galaxies, right? Okay, but the point is that we have seen this sign here. Okay, so then let's see how this were looking like. These were snapshots from our simulation, and then the referee said, "Okay, okay, I look here. There is an m=2. It's not. No, I don't. I'm not convinced. I want you to put all the snapshots of the all together, and then see how it looks like." And we couldn't do that by that time, but we could do the other thing, and he was satisfied with that, or she, or I don't know who was the guy. We have Fourier analyzed our snapshots. We have taken the faces, and then it was just a few points that we could rotate, put on top of the other, and this is what you see here on the right-hand side. So there is a strong m=2 component that goes to the 4-to-1 resonance, and then weak, fainter extensions that go all the way further away to higher resonances. Again, so the point I already mentioned, what was the criticism? First of all, it's two-dimensional. Second, and most important, people hated hearing about that, is that we had a rigid halo. The halo was not alive. Okay, then the point was to use, we had a dream to use one day some of the popular n-body simulation codes and to see how this would work. And we did simulations. Actually, these simulations were for many years done, but it was the Periklis who came here and analyzed all that stuff in a very nice way, and we could look at it. These are gadget 3 simulations. So here we have a live halo, we have star formation, feedback, all possible mechanism acting.
And the black is the total rotation
The
curve, right?
black is the total rotation curve, and again, you cannot go away of that. Again, we have a balance between luminous and dark.
Is this with a maximal disk?
No, that's what I'm saying.
Okay.
We avoid this because if you assume a maximal disk, then you go immediately to the bar system. To delay the bar formation, then you give more to the dark matter in the inner parts. And then another important component that plays a role is the presence of a bulge. The bulge was present also to the old n-body simulations, is the red one that you see over there. And under these assumptions, we could find an evolution of the path. We have, first of all, we had an m=2 grand design bisymmetric spiral that has been evolved after, let's say, 1 year after the beginning of the simulation. And this is the evolution of the pattern speed we have calculated, as you see here. I have extended the axis, but okay, you can see that we have practically 2 phases of a bisymmetric spiral that is close to 23, let's say, kilometers per second per kiloparsec. It has a deep going down over here, then recovers going up there. During this jump, to a lower value, we don't see destruction of the grand design character of the spirals. It's there and it doesn't last so long. I don't know. We have to go to the details. There is also in this work in progress. We have seen that the behavior was very consistent, and since to find the results I'm just showing you today, we didn't run a single simulation, of course. So we had a series of simulations with low resolution, and these are low resolution simulations, just with 1 million particles altogether. And we have seen these are the two phases. So you see, the main thing is that you have this inner bisymmetric part of the spirals being present. Look, for instance, up. Sorry, managed to do that, but okay. Okay, here we are. I just wanted to go, for instance, in this snapshot. And then you see that somewhere here and there is something symmetric, then this is an extension does not exist in the other case. But then you also have these very nice bifurcations. In some cases are very reminiscent of the morphology of specific galaxies. We do not dare to overinterpret things, but really this snapshot here looks very close to the NGC 5247 where I was showing you before. But in many cases, you see something that it goes smoothly up to a point and then something happens and it's the spiral structure beyond that distance is getting more asymmetric, fainter, and all that stuff.
It's a two-dimensional.
No, this is three-dimensional, live halo.
It's gadget, it's everything.
It's everything, yeah. Of course, yeah.
Now, anyway.
Okay. And then we did the same analysis, and then it's exactly, we have seen very similar things as what we are looking at the simple n-body simulations. For instance, to the left, you can see that we have a component that it is the peak of which is between the 2-to-1, the 4-to-1 resonance. In the stars, you cannot see that very well, but the black spiral we have over there, it is the fitted spiral to the density of the disk of the stars. And if we go to the gas, we can see much more things. The pink circle here is the 4-to-1 resonance, and you see that the bisymmetric spiral somewhere ends here. Then you have these out of phase extensions and all that stuff. But in some cases there are also an n=2 component. We didn't check if it rotates with a different pattern speed, etc.
In general, the gas annoying as it is, simulations, because dissipative fluid, it settles in the potential minima and maxima much faster than the stars.
True.
Right?
Yeah, and exactly because it is dissipative component, then it is much better for presentations. Okay, here. So we have also, of course, integrated orbits. We have seen that it was that one. Yeah. So sorry. I have to go back again. Excuse me. Okay, here we are. Okay, here just to show you that, of course, here we are in an n-body simulation that you have seen that there is a variation in the omega, but it's not that important as to destroy the structures. And most important for us is to change the dynamics behind. So everything, all these morphological deformations we are expecting that the 4-to-1 resonance are there and are characterizing to a large extent the morphology of the galaxy. And here just to show you that in some cases we have an n=2 pattern that has its maximum strength between the 2 and the 4-to-1 resonance, and this is what we see is the spiral we see by eye, we identify, but then we have the extensions that they go down to lower levels of surface density, etc. They exist, or we can have some clumps of like what you see here. See here we have some, here is the main component, here is the part that corresponds to the spiral we have seen in the snapshots, but there these are also some other unequal two parts, not well organized, built a bisymmetric spiral pattern in a larger distance from the center. Here it is to the left, the amplitudes, the normalized amplitude of the component, and you see that the blue one characterizes the spiral we observe. And when you cross to the fourth one, resonance, you see how other Fourier terms are coming in the play, and then in taking them also into account, we have to try to explain the morphology beyond the fourth one resonance. And we are very much satisfied because, again, comparing with observations, we have also a nice agreement. You see that the maximum of the amplitude over there, it's about 20%. And the pitch angle was the one of the modes that we have found to be developed in our model was 16 degrees. And this is exactly what our analysis of near infrared observations of non-barred spiral galaxies also suggests that if you have a 16 degrees pitch angle, then this would be compatible with the 20% amplitude over here. We are somewhere here in the tangent of pitch angle. Okay, as I told you, this is a work in progress. So one of the things that we have not, this is published work, but this is not published yet. One of the things that we want to underline is that the results continue to hold for more high resolution simulations. Here is one example with one order of magnitude more particles than the one that I have shown you before. Not much difference. What you can see, however, here is that if you go to the stellar component, you can much easier see by eye by the end of the bisymmetric spiral. This is the stellar component and the Fourier analysis of that one and the corresponding snapshot for the gas. You see how much more structure you have over there, which is also a nice agreement between what you observe in the optical and in the near infrared. There is the same tendency, at least, to having the gas much more structure, let's say, bifurcations of the arms, of phase extensions to larger distances, etc. But exactly around 6 kiloparsec from the center is the a little bit less than 6 kiloparsec is the fourth one resonance, and you see that up to that point the blue curve dominates, the equal 2, and then all the other stuff is coming after that. So this is what I want to tell you. This is the summarizing here our conclusions. The main conclusion is the one on the first line, that this non-bar grand design morphologies appear also in self-consistent simulations. You don't need to go by hand and give it there. They last for something like, in the simulation I have shown you, it is for 2.5 gigayears. We had the non-barred grand design phase. Things improve in higher resolution models, but I will speak about that when we have the results. Also, the motivation for doing now this study was to see, to investigate what happens with the fourth one resonance. And we have seen that also in these n-body simulations, in this new environment, we don't have analytics simulations, we have parameters that vary, like the pattern speed, like obviously, let's say, I don't know, maybe the mass changes and all that stuff. But under all these assumptions, they are not that severe as to change the dynamics we have seen in the analytic models. The dynamics of this phase, this is actually what we want to underline, is that is consistent with the 4-to-1 resonance dynamics. The orbits of the stars are around the center of the galaxy. They cross the spirals. And there is also finally something that we are working on to see how successive modes may act. We have seen in the old days and body simulations that if we have studied not the bisymmetric inner part, but farther out M-equal modes that existed in some cases, we have seen that they were following the same dynamics. They were also ending close to their 4-to-1 resonance. So we want also to see if we can identify this double kind of pattern speeds and what are the dynamics of them in these cases. So more or less, I think this was what I want to tell you. Thank you. Time for the panel. So if there are questions, yes, let me also. Yeah, I hear.
Something which I think is important, if generally true. You're telling me that if you actually make maximal L over M disk decomposition, you end up with bars very fast. Is this a generic result?
It's a generic result. It was obvious from the very first days of the n-body simulations.
Because when I was talking with Daniel Fenninger, and sometimes where we talk about this decomposition and how much dark matter you could have it, there used to be a degeneracy of the L over M that people could do with pure kinematics, pure rotation curve decompositions. So in this case, you are kind of breaking that degeneracy, saying, look, the moment you're going to put a maximal L over M, you're going to get a bar too quickly, and that doesn't happen. Is this published as a standalone thing, or is it kind of permits the work around?
No, I said we delay the bar.
No, I'm saying delay. Yeah, the delay.
So later, this one also develops a bar. And we have done a lot of things with the bar we found in after, let's say, 4 gigayears after the beginning of the model.
The galaxies will tell you we have non-bar ones, so you could use the data to say, I cannot have the bar too early because then all galaxies will appear barred. Then I will take them in a snapshot. One is ahead, one is behind, but if the bar appears early, they will all appear barred. So you can turn the argument around saying, I cannot have bar galaxies too early, therefore the L over M is such and such, or within that range.
It is not easy to answer it with this kind of models, because here we go, first of all, to investigate how the morphology of galaxies in the local universe is.
Yes,
so here we have 10% gas. Okay. Not only this, there are many, it's different behavior if you had 50% gas or I don't know. It is, there are things that behave differently. Right. And also the other thing is that, okay, it is an n-body model. All these nice features are there, the live halo, the star formation, the feedback, all that stuff, but it is a model. So for instance, we follow a model for, let's say, 8 gigayears, or I don't remember how long but certainly, for instance, we do not have black hole here in the center.
Well, I don't think that would be.
No, but things, all that for describing, let's say, a galaxy from the time it is formed to today, certainly you need to put more physics on this kind of models. Here we just simulate an environment like in the local universe, and then let's say if we have also all these additional features, how much would the dynamics differ from assuming a potential that doesn't change in time, and then we can control everything in the orbital theory, etc. How much? And the answer is that not that much. So the underlying dynamics is, I wouldn't say the same, but it's similar.
Very quickly, not monopolize the floor here. one of the other things which totally surprised me, you're telling me that if you have stationary potentials, you end up with certain features. The moment you go to gadget and you make it all live, the main features survive.
Yes.
This, if it's general, there must be a way to kind of show it analytically for the analytical people in the audience, right? Because it's one thing to kind of show it with simulation after simulation, but if it's a general, it's very important because it says even the dummy potentials, the ones which don't change with time, give you these features in the spiral patterns, all these things. If I make it alive, if I make the potential, responsive, let's say if it's time variable, the same features survive. This is it's huge.
You can build models. I'm saying semi-analytic models, whatever, that will have an effective, let's say, dependency of all that parameters that are introduced through the n-body simulation. For instance, very primitive investigations direction is to take. There are such papers. You say that, okay, I think that there is the mass of the bar component, for instance, increases with time. Okay, let me integrate orbits in such an environment and see. Okay, and then it looks that there are rules to make the correspondences, but that the pattern speed is another thing, and all that stuff. It is not a well-developed theory, let's say, in nonlinear dynamics that takes the time dependency into account. It has not been developed because it is difficult, I can tell you. And okay, there is of course room for.
The reason that the main events survive, even if we put time dependence on the field, isn't that just because the dynamical timescales of the variance of the potential is very large compared to the motions that.
I can say that. So what we find there is that the potential varies, but it's not varying very fast at this phase. Okay, we can say a word from what we have seen. It is that this model that we have studied at a certain point abruptly goes bar unstable, and then at this phase the potential varies very fast, and when you had a spiral in the same area of the disk, you have a bar. During this phase you have a very abrupt change of the potential, of course, right?
Then do the main pictures still survive?
No. Then you have a completely different morphology, if you want to speak in that term. You have a bar spiral system that continues existing. And as I was telling you before, if we had a black hole, a massive black hole in the center, we could do other things with the evolution of the bar, or I don't know, other things that one has to take into account. We do not describe here the life of a galaxy from the beginning of its formation to today. No, we have a model. And we're just looking, for instance.
Yes.
We local dynamics and trying to put more physics in the analytic models. Making one step, what we report it to you.
One thing in the 2D simulations in which you said that they didn't like it because it was not detailed enough. Which algorithm did you use?
By that time, it was a grid-based algorithm that was built.
What? I'm sorry?
Grid. A grid.
A grid-based.
Yeah.
Okay.
It's a grid-based algorithm.
A block-based.
A Eulerian code, if you want. Yeah, you have a polar grid, and then you did your calculations on the nodes of the grid.
Okay. Yeah.
2D. Well, it's a long story for this development of this code, I can tell you. So, are there any other questions? I don't see from the audience, and I don't see also, is there anybody who wants to ask? Okay, I don't think so. Then I think that's it, huh? Time for the party. Okay.
and meet for to continue.